Okay, so quadrupole moment we were talking, electrical quadrupole moment of deuteron and the measured values, experimental value was 2 point how much into what centimeter square. Though it is small when you compare with quadrupole moment of many other nuclei, but still it is significant, and it tells that the charge distribution is not spherically symmetric, and that means the this L equal to 0 alone is not the very correct description. So, it is mixed with L equal to 2, the same conclusion that we drew from the magnetic moment. Okay. So, if the angular momenta, orbital angular momenta are getting mixed up in the energy eigenstate, that means the Hamiltonian is, or the potential is not central potential. This nuclear interaction should have a non-central term. The other familiar situation where this non-central force comes in is when you consider interaction of two magnetic dipoles. If you have two magnetic dipoles, one dipole here and another dipole here. So, this is, let us say, the separation vector is r and the dipoles are oriented like this. So, these dipoles will exert forces on each other. So, there will be some potential, corresponding potential energy you can write. Then the same dipoles you can arrange in other fashions like this or like this. So, the force between these two dipoles and force between these two dipoles and force between these two dipoles are different. So, this separation vector r, as it changes its orientation, you can fix up some z axis and x y and theta phi r theta phi. So, the force is depending on theta phi, depending on angles. If the dipoles are placed this way, so the r vector is this way, force is different, same separation, same magnitude of separation, same number of centimeters. But if you put the, if you just orient it in a different fashion, so that r vector is now this, same separation. So, in r theta phi, r remains same, theta phi changes, but the force changes. So, this is one kind of non-central force, and if you write the magnetic energy corresponding to this dipole-dipole interaction, that turns out to be 3 times m1 dot r and then m2 dot r divided by r square. This is unit vector r here in fact, and then minus m1 dot m2, some constants, something like this. So, taking clue from here, people write the non-central part of the nuclear potential of nucleon potential as 3 times sigma 1 dot r sigma 2 dot r divided by r square and minus sigma 1 dot sigma 2, and this whole thing is to be multiplied by some r dependent part. Okay. So, this type, there are many other terms which one has to bring in to really explain all the experimental data. If you try to write the potential between nucleon and nucleon, it is a long expression, right. You had seen a central part, the spin independent central part, that was the basic square wave potential that we considered. On that spin dependent part, P sigma, and now the non-central part, and then there are more terms also. So, it is a long expression. Okay. So, this much we learned from what we call deuteron bound state. Okay. Now, the next phase is, you can also learn about this interaction from the scattering states. That means, it is not bound, but it interacts and goes. Okay. So, how that interacts, and that will result in different distribution of scattered particles, and from there you can derive information about the interaction. So, in a scattering, the geometry is something like that. You have some kind of material which you call target, and then you send beam that you call projectile, normally a parallel beam of projectile particles are sent and they hit this target material, and energy is controllable. So, you give some kinetic energy, fixed kinetic energy of these projectile particles. Then from this target, in the target you have scattering centers, because in any experiment you will not put one proton or one molecule or one atom, right. When you are doing the experiment in the lab, you have to put some foil or some plate or some gas or something that will have many centers. So, what we are trying to work out is NP scattering. So, here you will have a target containing hydrogen, and the nuclei, the protons will be the scattering centers that will be fixed here in the target, and neutrons will come from one side. So, the projectile particles are neutron, but any scattering experiment you have a projectile beam. Normally, the kinetic energy of each particle in the projectile is controlled, tuned. So, they are monoenergetic particles falling on the target, and target has number of scattering centers. Each one can interact with each one here. Okay. So, depending on which projectile particle is going close to a particular target scattering center, that interaction will take place in that event, right. So, this way. Now, on the other side of this, you put a detector. Normally, this is quite small. This beam size is maybe say 1 millimeter or even less. Nowadays, you have micro beams where the accelerator gives you a beam of ions which can be focused to say 1 micron or even less, 10 to the minus 3 millimeters, 1/1000 of a millimeter. So, you can have very focused ion beam, right. So, those things are there, but typically say a millimeter or less. So, although I am drawing the diagram, this is not to the scale, but this portion is very small and this thickness is also normally small. So, you put your detector somewhere at some angle. So, if the particle are going in this direction, this detector will pick it up, and this you take as z axis, and this angle is theta. You can also change phi, but normally the scattering is independent of phi, it depends only on theta in this type of geometry. So, for different values of theta, that means you put detector here, you can put detector here, you can put detector here, here and so on, and you get the distribution of scattered particles. How many particles are going at this theta, how many particles are going at that theta, how many particles are going at that theta, and so on. So, this is the experiment. That data is analyzed, and whatever information about this interaction is needed, that is derived. Okay. So, the number of particles at a particular theta, there are some trivial dependencies. Trivial dependencies like, suppose I collect this data for 5 minutes, and in the next experiment I collect the data for 2 minutes. So, we know that in the second experiment we will get less number of particles, we have done only for 2 minutes. In the previous experiment we did it for 5 minutes. So, it is an obvious dependence, right, trivial dependence on time. It has to be proportional to time. More time you allow for data collection, more number of particles will be collected. Similarly, other is how big is, because these are particles are going in all directions, not equally, some directions are preferred, some directions are less preferred, and so on. But in this direction itself, suppose your detector is placed at double of the distance, right. In first experiment you put the detector here, in the second experiment you put the detector at double the distance. So, if these lines are diverging like this and you put the detector at double the distance, so less number of particles will enter that area of the detector. Okay. So, the solid angle subtended by that detector on the point on the target from where the beam is coming, it will be proportional to that, because it is going in all directions, in all angles. So, if you pick up a small cone, there are certain particles going there. Now, if this solid angle is increased, if your detector is placed close to the target or detector window is large, it will collect more particles. Okay. So, it is proportional to the solid angle. So, these are some obvious dependencies. So, let us say the dn, what is dn? Number of particles collected in the detector. This should be proportional to time, this should be proportional to d omega, okay. Then this should be proportional to the intensity of this projectile beam, okay. Intensity of the projectile beam, or sometimes it is called flux. That means how many particles per unit area per unit time are going in the beam. So, perpendicular to the beam direction, if I construct an area and look for certain time delta t, how many particles are crossing this area, right. Make it per unit area and per unit time, that is called intensity of the beam, number of particles crossing this perpendicular surface per unit area per unit time, that is intensity. So, if that intensity is increased, the dn will also increase, more number of particles are falling here. So, it is proportional to this I, intensity of the beam. Of the projectile beam, right, which is number of particles crossing unit area in unit time, and unit area does not mean 1 meter square. If you take 1 meter square, your beam is only going here, not in that entire thing. So, in the beam cross section, right, in the beam cross section, or you can take the whole beam cross section itself and then look how many particles are crossing it per unit time, divide by the beam cross section, that is intensity. And one more thing, since it is not one particle sitting here, it is a target. So, how many particles are there to scatter, how many scattering centers are there in the path of the beam, okay. This is the path of the beam. So, the particles can be scattered from here, 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 so on. So, how many target particles are there? Number of target particles. So, that number of target particles. So, these are trivial or obvious dependencies, it has to be proportional to that, whatever is the kind of interaction, right. But the proportionality constant, that is really related to the kind of interaction that the projectile particle and a target particle are having. So, you write this as dn is equal to either you use symbol d sigma d omega, or you use symbol sigma as a function of theta, theta phi. Let me write theta phi. This is the proportionality constant, and then all these things t, d omega, I, and number of target particles. Number of target particles is generally expressed as area of cross section of the beam, because only that much area is hit, right. Area of cross section of the beam, projectile beam, only that much area on this target surface is hit. Okay. So, areal density means in this entire target how many particles are here and divided by this area, that is called areal density. It is the actual density into thickness. So, areal density into area. So, N A, this is areal density, and into area. So, this is the number of target particles. So, it depends on the density there in the target and the thickness. So, it is this. We can combine this I, this A and this T. This becomes how many projectile particles are going through the target in that time, because I is number of particles going per unit area per unit time, and here is area and here is time. So, multiply by that. So, this is the number of projectile particles which are hitting the target. So, you can write in terms of that also, it is sigma theta phi and then d omega and this N A, areal density, and the number of projectile particles hitting the target. So, sigma theta phi is d n divided by d omega N A and N P. So, this is how, and this is called differential cross section. This is called differential scattering cross section. And this contains the information about the kind of force, the kind of potential, the kind of interaction which is taking place. All the geometrical factors we have already taken out. So, this is purely, it is representing the kind of interaction which is taking place when the projectile and target particles are close to each other, right, which causes a scattering. So, this experimental arrangement allows you to measure this cross section. You measure dn, you count how many particles are going there at that particular theta phi. So, dn is there, then you have placed the detector at some distance and there is some area of the detector window. So, you know d omega, how much is d omega, and then areal density, what target you are using, what is the density of that, what is thickness of that, number of projectile particles during your experiments, whatever time you have allowed, how many projectile particles are hitting. So, all those things can be calculated, can be obtained, can be measured, counted, and from there experimentally you can obtain the scattering cross section. So, idea is do an experiment, find this cross section from the experiment, then the theory you have in mind, from that theory you derive what should be the cross section, and then match and see whether your model, your theory, your calculations are correctly reproducing that cross section or not. and then you can adjust the parameters, you can change the model, you can modify it, you can do something else and come out with some good theory which is consistent with the measured results. So, that is the game. Okay. Fine. So, the whole purpose was to tell you how people do this experiment, starting from Rutherford alpha particle scattering and lots of in atomic physics, nuclear physics, scattering experiments are done abundantly even now. Right. So, this basic formulation, the basic meaning of this cross section, every time you will hear this word cross section for this interaction, cross section for scattering, cross section for capture, cross section for absorption, so many things. So, this is it. You can look at the unit of it or dimensions of it. This is number, this is angle, solid angle, and this is again number. So, it is 1 by N A areal density, number of particles per unit area. Okay. Per unit area. So, this is area inverse, and since itself this is in denominator, this whole thing has dimensions of area. So, the cross section, the values of cross section will be quoted in units of area, and 10 to the power minus 24 centimeter square, which is 10 to the power minus 28 meter square. That is this is a kind of order of this cross section. So, this is given another name and is called what? So, cross sections are generally quoted in these units. So, let us see from the this neutron proton thing, what do we expect if we assume that square well potential and so on. So, again some basics of scattering by central potential. So, here is the origin, and then you have a central potential, that means the interaction between the projectile particle and the target particle is represented by a potential which depends on only r, not on theta phi, central potential. Okay. So, if the particle is coming and then getting scattered, what how we calculate from theory the scattering cross section for central potential. Now, if this potential is not there and only the beam is coming, then there will be no scattering, the beam will just go, and then the wave function will be like e to the power I k z. Z is the direction of the beam, and what is k? Right. Free particle going in z direction with an energy capital E is represented by this wave function. Right. You can write the Hamiltonian and H psi equal to E psi, no potential energy term, only kinetic energy term, and from there you can work out. So, a particle which is going in z direction with energy E will have this wave function, free particle wave function. So, if there is no scattering center, right, if there is no scattering, no potential, 0 V is equal to 0 everywhere, then this is the wave function. Now, since we have to work with scattering and this is the geometry, so put up origin here and then as a function of theta phi we are measuring the number of counts and all that. So, we can write this as in terms of theta phi, in terms of r theta phi. So, this as such this is e to the power I k r cos theta. Okay. And in this, what is the linear momentum? Linear momentum P is h cross k. So, if you have fixed the energy, k is fixed, and this linear momentum is also fixed k, and this is h cross k in z cap direction. So, if the energy is fixed, this k also gets fixed, and if this k gets fixed, then h cross k, that means the linear momentum is also fixed. So, if you write the wave function in this form, it is a simultaneous eigenfunction of the Hamiltonian, because energy is fixed, and linear momentum operator, because the linear momentum is also fixed. What about angular momentum? This is not an eigenfunction of angular momentum operator. So, this same state of the particle, if you ask what is the linear momentum, I have a definite answer, this is the linear momentum. But if you ask what is its angular momentum about that origin, it is not a definite angular momentum state, it has got several angular momenta simultaneously present, right. Leaving out spin part, the angular momentum corresponding to this motion. So, small l equal to 0, small equal to 1, small equal to 2, 3, they are all mixed up to make this state. Okay. You know, if L is equal to 0, you should have some r dependence, and theta phi dependence should be y 0 0. Right? L is equal to 0, m equal to 0. If L is equal to 1, then you will have several states, m L is equal to 1 and 0 and minus 1 and so on, and this will be some function into y L m L. So, all those things are there, and our wave function is not of that type, right. This wave function is not of that type. So, it does not have a fixed angular momentum, it is not L equal to 0, it is not L equal to 1, it is not L equal to 2, but it is a superposition of those L equal to 0, L equal to 1, L equal to 3, L equal to 4 and so on. So, in what proportion do I superpose them to get that? So, that expansion can be done, and when you do that, this e to the power I k z can be written in terms of this. First thing you can see, there is no phi dependence here, it is only theta dependence, and in YLMs, if this m L equal to 0, then you do not have phi, but if m L is there, you have e to the power I m L phi, right. This y L m L, which is a function of theta phi, it is some constant, then this P L Legendre P L m L cos theta, and then you have e to the power I m L phi. So, if it does not contain any phi, that means all these m L should be 0, because if m L is not 0, you will have phi dependence. So, in making these combinations, only those m L equal to 0 terms are to be taken, L equal to 0, 1, 2, 3, 4 you will be taking. This turns out to be summation over L going from 0 to infinity, then I to the power L 2L plus 1, okay, and then some Bessel function coming in JL KR and PL cos theta, ML equal to 0. The expansions are standard procedure. If you know this, you first write as some constant time, and then this is PL cos theta and so on, and then you have to do an integration to go get that constant, and then you can derive these expressions. So, if there is no potential involved, no interaction involved, then the wave function will be of this type, but there is an interaction. So, the wave function will not be this, will be something different, right. Now, if a detector is placed here and I am taking the particles here, and this target atom or target nucleus is here, and the projectile particle is coming and getting scattered from here, whatever, this way or that way or this way, in whatever kind of interaction it is. Look at the distances. This range of potential, in nuclear case it will be in femtometers. If this separation is say 20 femtometers, then almost no interaction. So, whatever interaction is taking place, that is taking place in femtometers, or if it is atomic case, atomic collision case, this could be in angstroms, right. Whereas, the detector you will be placing at least few centimeters. Okay. So, this distance is very large as compared to whatever r you will be writing for that interaction. So, we are interested in the wave function, or what we can access, right. We can access to wave functions at large values of r, right. What is the wave function right here? I do not have probe to go there and look at that. Our detector will find the particles only at large values of r. What happens when r goes to infinity? What happens to this JLKR? This JLKR turns out to be, it goes as sine of KR minus L pi by 2, right, very good, divided by KR. That is how it goes. So, you can write this wave function as summation over L and I power L 2L plus 1, and then sine of KR minus L pi by 2 divided by KR, and then Legendre polynomials. It turns out that when you have the potential, you have the interaction, this wave function will get modified, and the modified wave function can be written almost in the same format, with one difference, that all these sign arguments here, they are changed by certain amount, and that change, that extra phase term coming here will be dependent on L. For L equal to 0, that term could be different, L equal to 1 term can be different, and so on. So, the wave function that you write in presence of potential, the one which is already written is when you have no potential, it is just e to the power I k z that we have expanded. Now, if the potential is present, if the interaction is present, then this will be just changed to your psi will be changed to L equal to 0 to infinity, and all those terms will be there, and sine k r minus L pi by 2 plus delta L, some delta L will be there, divided by k r P L cos theta. Remember, these things I am writing for large R. Okay. These delta L are called phase shifts. So, effect of this interaction is hidden in this delta L, all right. these are related to what kind of interaction is there, and these therefore, these delta L's must be connected to the scattering cross section. Okay. Scattering cross section gives you the strength of scattering, the interaction between the target material and the projectile material, okay, in each event, and the effect of interaction is in delta L. Therefore, the scattering cross section must be related to this delta L, and that expression turns out to be sigma theta is equal to 1 by k square. K, you remember what is k? L going from 0 to infinity, 2 L plus 1 e to the power I delta L sin delta L P L cos theta and then square, right? This whole thing is square. So, now what is the next task? Next task is start with the central potential that you assume that you want to try out. Take a central potential which you think is the potential corresponding to neutron proton interaction, neutron proton force. With that potential, do some quantum mechanics and get delta L, and from there you get the scattering cross section and compare with the result there. Okay. So, we will now do that. So, you get contribution from all these L equal to 0, 1, 2, 3, 4 and so on. But then if energies are small, you do not really get significant contribution from too many angular momenta. Okay. For very low energy, only L equal to 0 will be significant, L equal to 1, 2, 3, 4, all the contribution will be negligible. If you have somewhat higher energy, maybe L equal to 1 will start contributing significantly. So, it is not that you really have to add large number of terms here, and we can make a small semi classical calculation to look at that energy angular momentum relation. Suppose you have the particle here, target particle here, and the projectile particle is coming like this, and the nuclear range is r naught, the interaction range is r naught, distance r naught. So, that means in this region when the particle reaches, then there will be some interaction, but if the particle goes like this, then there is no interaction, it just goes straight. So, for really scattering to happen, this particle must go into this sphere. So, the range is, let us say, r naught, right. Now, let me take energy of this, this is say proton here and neutron is coming and going like this, and energy is say 1 MeV. Let us try to calculate the angular momentum using our classical picture, particle going like this. So, if this distance is r, right, if this distance is r, the angular momentum will be m times v times r, p into r. Okay. Now, this p is square root of 2 times m times the kinetic energy and then r. Let us take it at the edge. I want to have maximum value of linear momentum for which the scattering may occur. The angular momentum may be this distance multiplied by linear momentum, but then the scattering will not occur. So, I am taking this r naught. So, take it r naught. What is this E? Kinetic energy. right. This is P square by 2m is kinetic energy. So, I am using classical picture. So, 2 me times this. Now, what is this? 2 times mass of the particle, mass of this proton is some 938 MeV or so. So, let me write it as 1000 MeV to make a quick calculations, and mass is MeV by c square. Right, because mc square is 938 MeV, right, proton rest mass energy. So, mc square is 938 MeV. So, m is 938 MeV by c square. So, this MeV by c square, and energy, let us kinetic energy, let us take 1 MeV. So, it is just 1 MeV, and into R naught. R naught, how much R naught I should take? Say 2 femtometers. Okay. So, let us work it out. This will be square root of 2000 MeV by C, MeV by C, MeV by C, and into 2 and femtometers. That is the angular momentum. Okay. So, let us work out what is L by H cross, because if L is equal to 1, L square is 1 plus 1 H cross square, that is 2 H cross square. So, L square, let us write L square, why to do square root? L square by H cross square, L square by H cross square should be 2. If L is 1, this should be 2. So, let us work out how much is this. This is 2000 into 4, 8000, right, divided by H cross square, C square, MeV square, femtometer square. Now, how much is this H cross C? Hc you remember, H into C, 1240 MeV femtometer. So, H cross means divide by 2 pi, divide by 2 pi. So, 3 into 2 is 6. So, about 200, about 200. So, this is 8000 divided by 200, square of that. So, 40000 and MeV for me square, right, and here also MeV femtometer square. So, that cancels out, its number, it should be number, it should be number, it is coming out to be number. How much it is? 1 by 5. So, instead of 2, what you are getting is 0.2. So, that means L equal to 1 is not at all present, because L equal to 1 will happen if the angular momentum square is 2 H cross square, and with this kinetic energy of 1 mega electron volt, the angular momentum, so that it goes into the range, and that distance you cannot increase, 2 femtometer is the range, nuclear range. So, it has to be that R has to be less than 2 femtometer, and kinetic energy is fixed 1 MeV. So, linear momentum is fixed. So, you cannot increase the angular momentum with these parameters. You can increase the particle, you can take it at a larger distance, but then the scattering will not take place. So, for scattering to take place with 1 mega electron volt particles, L has to be much smaller than that the root 2 H or so, and the only value which is available less than root 2 H in quantum mechanics is 0, L equal to 0 or L equal to 1, there is nothing in between. So, if you are not able to reach L equal to 1, you are in L equal to 0, right. If it is 10 MeV, if you take this as 10 MeV, So, it will be multiplied by 10, right here. Instead of this 1 MeV, if you take 10 MeV, so that means this will be 2. So, around 10 MeV etc. This, of course, this calculation is very approximate and classical type and semi classical type and this and that, but this tells that 10 MeV, if you are 10 MeV kinetic energy particles if you are sending, then worry about L equal to 1. 1 MeV is very safe. If we are lower than 1 MeV, so even if this model is approximate and we are using classical physics arguments and calculations and quantum mechanically this is not true and so on, but then giving all the margins, if I say that I am confined, my kinetic energy will be less than 1 mega electron volts, then we are very safe to say that only L equal to 0 will contribute to the scattering. Now, if you do that, L equal to 0, low energy scattering. So, for low energy scattering, and low energy scattering means E less than 1 MeV, let us say. This sigma theta will be 1 by k square. Now, L equal to 0 to infinity, I only need L equal to 0 term, and L is equal to 0. So, this 2L plus 1 is 1, and since there is no summation, no more summation, only L equal to 0 term we are looking at, this e to the power I delta L, when you do this mod square will become 1, e to the power I delta L, mod square of that. So, multiplied by its complex conjugate e to the power minus I delta L. So, that will become 1. So, sin square delta L, sin square delta 0, L equal to 0, and L is equal to 0, that first Legendre polynomial is 1. So, this is also 1. So, that is it. Okay. This differential cross section will be obtained just 1 by k square. This k is related to energy, kinetic energy, square root of 2 m E by h cross square, and then sin square delta E, delta 0. So, if you can get this delta 0 from theory and this delta 0 from experiment, because differential total cross section you can write total, all theta phi integrated. Since in this you do not have any theta phi, in this expression you do not have any theta phi, theta is coming from here. Normally it should depend on theta, and that dependence is here, but if you are in low energy, so that only L equal to 0 is operative, then there is no theta dependence, it is isotropic, the scattering is isotropic, and in that case the total will be just integrate over all solid angles. So, 4 pi. So, this quantity can be obtained from theory and also from experiment, and then compare, and what do we check? The theory is correct or wrong, that we are checking, or the experiment is correct or wrong, that we are checking. Suppose this it does not match, I work out from theory that cross section should be this much, and then I take data from the experiment and find that cross section is this much, and these two are not matching. Theory we have to look at, the experiment is experiment, make sure that you have done the experiment carefully, but once you have done it carefully, it is repeated and same results are coming and all those things are taken care of. Work out your theories to explain that result. So, let us see if we can, the potential between neutron and proton that gave us deuteron bound state. If I use that potential, that interaction, what value of sigma do I expect? for V naught square well potential, V naught is equal to 36 MeV and R naught equal to 2.1 femtometer. Square well potential V is minus V naught for R less than R naught and is equal to 0, R greater than R naught. This potential was able to give me the correct energy, bound state energy. Can this potential give me correct scattering cross section at energies of say few kilo electron volt or few 100 kilo electron volts? So, work out the theory. How do you work out? First, if you do not, first thing is that since we are in low energy region, we will only be talking of L equal to 0, right. And if L is equal to 0, then your Schrodinger equation H psi equal to E psi. H is you can write psi as the R part and times y Lm cos theta, y Lm theta phi. So, that theta phi part is spherical harmonics, you know that for central potential, and this part radial part is u by r, u by r. So, you define u in this fashion y Lm, and this u, and of course, since we are doing L equal to 0, this is going to be constant, and for u your differential equation is minus h cross by 2m s square by 2m d2u dr square plus v r plus L is 0, okay, L is 0, okay, let me write first LL plus 1 h cross square by 2m r square times u is equal to EU. And then L is 0, so it is minus h cross square by 2m d2u dr square and plus Vr, u is equal to EU. So, there are two regions r less than r naught where V is equal to minus V naught. So, you have minus h cross square by 2m d2u dr square and minus V naught u is equal to EU. So, h cross square by 2m d2u dr square is equal to minus V naught plus E times u, correct. This is with minus and this is also with minus. So, this V naught remember is positive quantity 36 MeV and E is also positive quantity. We are talking of scattering, not of bound state. So, we are sending the proton with some kinetic energy. So, that is E, okay. So, this is also positive. So, this thing is now d2u dr square and equal to minus capital K square, let me write it capital K square u, where capital K is square root of 2m V naught plus E over h cross square, right. 2m over h cross I bring it here, minus I am keeping outside, and this thing is capital K square. And then you know the relations, solution u is equal to a sin capital K r plus b cos capital K r you can write, but then you have boundary condition at r equal to 0, u is equal to 0. From where this is coming? This is coming from this very definition, your radial part is u divided by r, and this has to be finite everywhere. So, at r equal to 0, this u should be 0, only then it can be finite. So, and that gives you b is equal to 0. So, u is a sin k r. and for the other region r greater than r naught, what happens? V is 0, okay, the potential is 0. For r greater than r naught, V is equal to 0. So, V is 0 is, put V 0 here. So, you have d2u dr square is equal to minus small k square u, where small k is square root of 2 m e over h cross square. So, just I am putting this V naught equal to 0. So, you get this, and here also your solutions will be like u is equal to some c sin small k r plus some d small k r. This region does not contain r equal to 0. So, both terms can be present. You can write this as some other constant, give any name E, no, E is energy, something, some constant. Let me write it as small c or okay, small c, although it looks similar, but does not matter, sin k r plus delta, right. So, outside it will be this and inside it will be this, where capital K is given by this expression here and small k is given by this expression here. So, remember these things. We will start from here next lecture. This r greater than r naught, u is this, r less than r naught, u is this. We will do that matching conditions, slope should be continuous and the value should be continuous, and that will give me the phase shift delta. Okay.